So today's lesson was about work, power, and efficiency. And I'd like to take a few minutes to go through those terms, and then we will go through a couple of math problems, and then you'll have some homework this evening. So the first thing that we should probably define is what power actually is. Power is the rate at which work is being done. Power is measured in the unit we call watts. So, for example, suppose you and your friend move a 50 kilogram box from the first floor to the second floor, and that distance is 3 meters. Your friend manages to move the box in 5 seconds, and you manage to move the box in 3 seconds. The first thing I want to ask is, do you do the same amount of work? Which one of you does more work? Or is there no difference? And the answer is that you both have done the same amount of work, but because you did it faster, you had more power. And so since the definition, again, of power is the rate at which work is being done, it's really taking a look at how fast work is being accomplished. So there is an equation, and the equation for power is equal to W over T, where P is power, and that's measured in watts. W, as we talked about in the second unit from the first semester, is work, and work is measured in joules. And then lastly, T is time, and that is measured in seconds. Okay. So if we were to apply that to an example problem, over here I say that a friend of yours applies 1,470 joules to a box for 5 seconds. How much power did they use? Well, in this case, the formula would be power is equal to work over time. So the amount of work was 1,470 joules, and the time was 5 seconds. And when I put that in the calculator and I get a value, the answer is 294 watts. So all that that's really telling me is that if I take the amount of work divided by the amount of time, I can determine the power. And some of you have become pretty excited or like the idea of using a triangle of fun when you can. And so for this particular equation, we do have the ability to do that, where P is equal to work over time. Again, I won't be giving you the triangle of fun on the test or a quiz, but I will. You have the ability to draw it. I will definitely give you the formula though. So here's another example that is a lot like what you would see on your homework. So in this particular instance, you have a forklift that is going to be lifting a 50 kilogram box off the ground, and the forklift happens to be electric. So the first thing I want you to do is to draw an energy bar chart with the box as the system. And so initially, the box is on the ground, not moving, and so that means the box has no energy. Finally, the box is lifted above the ground and is not moving. So it does have some energy, but it's a very specific type of energy. So in this case right here, we know that the box is above the ground, it's not moving, so it's going to have some gravitational energy. Okay, could have 4 bars, 2 bars, doesn't really matter. But how did the box get lifted off the ground? And remember, the box got lifted by the forklift. So that means that the forklift did work on the box. So if I was to write the energy equation for this particular problem, I would say that the energy equation is 0 plus work equals gravitational energy. And once upon a time, last semester, we talked about gravitational energy and all the other types of formulas that went along with it, so I should probably refresh your memory. EG is equal to mass times, let's see, sure, we'll do that. Mass times gravity times, where is it now? Shoot. Mass times gravity times height, okay? Where gravity was equal to 9.8 meters per second per second. We also had kinetic energy as a formula. And from that formula, we learned that it was 1/2 times the mass times velocity squared. And you're going to need those formulas for your homework tonight. But for tonight, or for this particular problem right here, I need to be able to identify what I have and what I don't have. So work is what I'm trying to find. Mass, gravity, and height are the things I need to deal with. So I know that from the problem that the height is 2 meters. I know that the mass is 50 kilograms, and we determined that the gravity is 9.8 meters per second per second. So when I go to fill this formula out, it's going to really be work is equal to mass times gravity times height. So to substitute in, it's going to be 50 kilograms times 9.8 meters per second times 2 meters. And when I plug all of that in to the calculator, I get a value of 980 joules. So that's the amount of work that's put in. So the third step to the type of problem that you're going to see for homework tonight is to calculate how much power the forklift requires. So if we remember back to just before, that power was equal to work divided by time. So this formula is asking us to solve for power. We just calculated work, and the problem gives us information about time. So in this case, the problem is telling us that the time is 15 seconds, and the work we just calculated up here, which was 980 joules. So this is not too bad. I'm going to take the 980 joules, and I'm going to divide it by the 15 seconds. And when I plug that in my calculator spits out an answer of 65.3 watts. So that's an example of a type of problem that you're going to see tonight where it was a two-step problem. We brought some stuff back from the first semester. Up here a second. Is this number right here. So that's really going to be my P out, my power out. Sorry, I got carried away. My bad. It's not the 980 that we're looking at here. It's the 65.3. That's my power out. And then the last thing that we need to talk about today is efficiency. So, where is my efficiency color? Shoot. Sad ass. So, efficiency is the ratio of the useful power output to the sorry. To the power input. Nope. So what that tells me is that whenever energy changes form, so for example, E chem changes to EK, some energy is lost, and that energy is lost through dissipation. We talked about dissipated energy last semester a little bit. But what efficiency tells us is how much of that energy is actually not lost by the system. So there is a formula associated with that, and the formula associated with efficiency is EFF is equal to power out divided by power in. And I usually say it's times 100, and I'll explain why in a minute. But something that we have to be careful about oh boy, I didn't even spell that right at all. Be careful about is percentages versus decimal. And I'll show you what that means in a minute. So an example of how to use the efficiency formula is that if the forklift from the previous problem, so the one that we just completed, uses 300 watts of power, that's the power in, what is the efficiency? Well, in this case, we were just told in the problem that the power in is 300 watts, but the power out, and I need 980, that 980 joules is my power out. So when I take that 980 and I put it into the efficiency formula, I'm sorry, not joules, that's, sorry if you were writing in pen, I apologize. I just made a mistake, got a little excited, happens all the time. So this is really 65.3 watts. So the 65.3 watts goes on top, and that's going to be divided by the power in, which in this case is 300 watts. And when I do that, I get a value of 0.22 times 100 which gives me 22%. Now, let me explain what that 22% means, because that's kind of important, actually. So 22% efficiency means that 22% of the power of the forklift went into lifting the box. That means that a lot of power was wasted, not used, something along those lines. So the closer your efficiency is to 100, the better you are in terms of the machine doing the work for you. So in this case, it really wasn't a great use of the power or of the machine, but it still got the job done. So your homework is to complete worksheet number 4, which is work, power, and efficiency. That will be due tomorrow, and hopefully you'll find it pretty easy. So good luck with that, and good night.